Assume it's recording. Hopefully. Okay, so this is on 1.2.3, and I think this first one is on the second page. The biggest thing is you're going to use Ohm's law for all of these, which is V equals IR. V equals I times R, and V is volts. That's the power. I is current, and that's measured in amps. And R is resistance, and that's measured in ohms. This is Miss Green. Okay. Okay, so on the first one, they're just asking, the flashlight uses a 6-volt battery, so our voltage is 6, okay? And it has a resistance of 150 ohms, so the resistance is 150. And they're just asking you to find the current, which is your amps, or I.
0.04.
Yeah. So we're finding I on this.
I'm assuming it'd be 40 milliamps.
Okay, so substitute the 6. We don't know I. There's 150. Divide by 150. So that's the biggest thing on this. A lot of you guys want to do 150 divided by 6 because you think you should always take the big number and divide it by the small number. Okay, it's okay to get decimals. All right. So the current, what did you guys get? Is 0.04 amps.
Does that mean milliamps?
Though that is 0.04 amps.
No, the 40.
It would be 40 milliamps. Yeah.
Yeah,
40
that's what 40
milliamps.
is.
Yeah. Okay. Now that's just like one light bulb, so they only had one kind of circuit. So where it gets a little bit crazier is when you start putting more than one thing in the circuit, right? So we've got series circuits and then parallel circuits. So the next one we're going to do is down here on the bottom of 1.21, just right across from the one you just did. So this is a series circuit. And I really feel like a chart is helpful when you do parallel or series. The biggest thing that you want to remember in a series circuit is that your voltages, the total voltage, is equal to the sum of all the voltages. But the total current is basically consistent throughout a series circuit. This is Miss Gray. I do. Yeah, he's taking some notes. He may or may not want to come because we're doing a workshop, but I'll. Okay, all right, thanks. Okay. So, and then on resistance, it's also the sum. So you need to know that for your test. Like, you need to know in series that voltages add up to be the total, but that current is always equal. So if you know one current, you know it all. All right? So that's really, really helpful. Okay, so definitely keep that in mind. So we're going to make a chart for this, and I always just make a V equals IR chart, kind of like that. And I've got 1, 2, 3, and a total. Okay, so I've got a 1, a 2, a 3, and a total down here. Okay. So at 1, we only know that the resistance is 220 ohms. So I'm going to go ahead and put 220 ohms on the number 1 on my chart. Okay. At 2, we only know the resistance as well. It's 470 ohms. Now here's where I want you to be careful, and please be careful on the test when you're taking this. This one, 1.2 kilo ohms. So I automatically go on and change that. Kilo means 1,000. So I'm moving my decimal 3 places to the right. So it's 1,200 ohms. Kilo ohms is the same thing as 1,000 ohms. So it's 1,200 ohms here. Everybody understand where I got that? We don't know anything else at 3. But on the total, we know that the voltage is 12.
For the rest of it.
Okay? Now, the reason I like the chart is it helps me visually see what I can figure out now. Knowing what I am given, now I can look and go, oh, I can figure something out. What do you guys think I can figure out right here?
Total resistance.
Total resistance, because resistance total is just these 3 added up. So I'm going to add those 3 up. So 1890. So 1,890 ohms is the total resistance. Okay, now I'm like, okay, now I can look across and I can see that I've got only one thing missing on this total line now. Does that make sense? So because I only have current missing, I can plug it into the Ohm's law formula. So basically, these lines going across, Ohm's law will always work. So this voltage should equal this current times this resistance. Okay, stop me if you don't understand. Okay, so I'm going to find out that current. So I'm going to say 12 should be equal to the I times 1,890. And then I can divide by, make sure you divide by whatever's with the I. No. So it's going to be a really small decimal, right? 0.006 amps. Okay, so that's 0.006. By the way, that is the same thing as 6 milliamps. Okay, so on the test, there might be a choice. You might get that number, but the choices might say 6 milliamps. You have to know that 0.006 amps is the same thing as 6 milliamps. Okay? Now, what do you know about current, though, in a series? Look. In a series circuit, current is always the same. So now that I know one current, I know them all. Make sense? I know all the currents now. Because in a series circuit, currents are always the same. Well, I can fill those in. And now I can use Ohm's law to find these voltages. Okay? So I just take the 220 times it by 0.006, right? Because voltage is equal to current times resistance. Okay? So 220 times 0.006, somebody. 130,
1.32.
1.32.
The answer's not exact because
That's fine. Okay, then 470 times, so everybody, I'm multiplying these.
2.82,
Thank you, 2.82,
7.2.
and then 7.2. Now, when you finish, please check yourself. Like, I took this test and I checked myself a lot just to make sure. So these should add up to something close to 12, right?
It's like
So it's kind of a good way to check and make sure you're right. So kind of add those up and make sure it's something close to 12. It may not be exact because we rounded. All right? But the chart is very helpful. Evan. Yeah. Okay. All right. So let's do a parallel now. All right. Let's go and do the parallel. So I think that's on the next page on your notes, guys. So what's different about a parallel circuit is this. Voltages are now equal to each other. So this is different than the series, so make sure you know the difference between parallel and series. You can tell it's a parallel because it's got these branches. Okay, that's a parallel circuit when you see the branches off. But current, you add them up. Resistance is weird on this one. Resistance is really, really weird on parallel. But this is why you'll also like the chart, because you may never have to use this weird thing. Okay? Resistance, the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. It's the reciprocal of the reciprocals, which is a pain in the royal rumpus, as we say in McLean County.
I don't remember. I know Mr. Humley showed us how to do it in calculator, but I don't remember.
All right. So that's what you got to remember about parallel. You got to know that before you get started. But we're going to make our chart again. So still the same chart. We've got 1, 2, 3, and a total again. So voltage, current, resistance. Okay, so we're going to fill in what we know. So we know resistance, 470 ohms. What about this resistance too? 2200, 2200, that's right.
There's some big better.
Right. Yep.
That would be 5,000.
I
Never mind, I'm afraid
can't add that. That's the reciprocal of the reciprocals. Now, I don't like to do reciprocal of reciprocals, so I'm going to skip it for a minute. Okay?
We know voltage is 15.
We know voltage is 15, and we know voltages
Constant.
are all constant. So all of these are 15.
We could use some simple math now.
So now we can find current for every line except the last one, right?
Yep. So let's do that.
Let's do that. Let's not do that reciprocal of the reciprocal thing. I want my life to be easy.
They know how to do this with a calculator.
Danny said he
30
forgot.
seconds.
Yeah, I forgot.
Okay, so So 15 equals I times 470. So divide by 470. So it's 0.03,
Yeah.
okay? And then this one will be 15 divided by 2,200, right? Does anybody need me to set that up? It's the same thing again. I'm just changing the number, right? What you got?
It's 0.0068.
So 0.007, you're saying? Okay. And here, 15 divided by 3,300.
0.005.
0.005. Is there anything I could figure out without having to do reciprocal of the reciprocals?
Yes, you can add all the i's together, and then you can get your r because
I'm going to find my total current now by just adding. Okay, so that's going to be 0.042. I just added 0.03, 0.007, 0.005, and I got 0.042.
You're saying just avoid the whole equation?
I'm avoiding this like the plague. It's not that bad, but I don't, whatever. If you like to do it, do it. So now I can find R by using Ohm's law instead of doing reciprocal of the reciprocal. Okay? So I'm going to do 15 equals 0.042 R. Divide both by 0.042.
356.
So the total resistance is 357 ohms. Okay? 357 ohms. There's no way 470, 2,200, and 3,300 add up to, and it shouldn't, right? Because this is a parallel circuit.
If it was a series, it would be 5,970.
If it was a series. Now, we can actually do 1 over 470 plus 1 over 2,200 plus 1 over, and you would get that. But I just usually like to avoid it. Okay? So that's parallel and series circuits. I believe that's all the math that's on that one, right? You've got the power formula, like power is work divided by time, right? Okay, so let's move to the work, power, and energy. We've only got 2 problems on that. The first one's really easy. Remember, work formula is force times distance, and it's parallel distance, not perpendicular. Perpendicular is torque. Now, here's the big problem on this one. Let's write down what we know. We know that the force is 50 pounds. And we know the distance is 4 feet. And we know the time is 5 seconds. And we're supposed to find the work. Now this is what I don't like about Project Lead the Way. All year they've been using English system. What did they ask for the work to be measured in? Joules. Guess what joules is? Newton meters. We don't have newtons or meters. Which means we're going to have to convert our pounds to newtons and our feet to meters. Like Project Lead the Way just all of a sudden decided they wanted everything to be a metric for this.
why it's meant to be superior, right?
I think I gave it to you in newtons and meters and not yes. I think. Okay? So somebody tell me, just Google, please, 50 pounds is how many newtons? And 4 feet is how many meters?
1 over 0.25 pounds.
I'm sorry?
50,
50 pounds is
1 Newton over 0.225 pounds.
over 0.225 meters. Oh, I see what you're telling me. 222 newtons. Yeah, you were giving me the one, I didn't introduce. 222 newtons,
0.5.
and then 0.4, okay? And then 4 feet is how many meters?
1.22.
1.22 meters. Okay, thank you. So now we can find work. And so the formula is not hard, just make sure everything's in Newton meters. So that's newtons and then times 1.22 meters. So work is 270.8 Newton meters, which is the same thing as 270.8 joules. Okay, it's the same. So just Newton meters is 1 joule. 1 Newton meter is 1. Okay? Now the last one definitely, I'm going to show you efficiency, and we're also going to talk about power.
I didn't finish filling out this one.
Okay. The same problem, but they just want us to find power.
Okay.
So all you have to do to find power is just the work divided by the time. So the work, 270.8 joules. The time was 5 seconds.
54.2.
So it's 54.2. And joules per second is the same thing as watts. 54.2 watts. Okay? Now, what I know is on the test that is not, there's not necessarily an example on here. So if I were you, I'd write it in this space over here. Let's do an efficiency problem. Okay? It's not hard. Let's do an efficiency problem just to make sure that everybody's on the same page here.
Which one?
How many times can we take? The can, say mini.
Yeah, it's even faster. That's good.
All right. So let's say that whatever electrical system that we use produces this amount of energy, okay? Let's say that it does produce that amount of energy. Would this be energy out or energy in? It's out because this is what we're getting out of the system. The energy in is going to be whatever the power is from the electricity. Does that make sense? The energy in is going to be what the electricity we're putting into it. So power for electricity, so you got two kinds of power. That was mechanical power, okay? And then you've got electrical power, and electrical power is P equals IV, current times voltage. So current times voltage, that's your electrical power. And that will be your in, because that's what you're putting into the system. We're putting the electricity into the system, and the electrical system is producing this.
Say that completes our circuit.
Okay? So let's just say that on our current, let's just say that the current in the system was 0.002 amps, and the voltage was, 12 volts. Okay? power, 24, right? And then 3 decimal places. Is it 0.024 or 0.24? 0.024. Okay. Back to it.
So do we use that for efficiency?
So efficiency is just your power in or your energy in, they're gonna call it, but that's the same thing as power. Okay? Your out, your energy, out over your energy in. So our energy out a minute ago,
So it would be 270.8 divided by
54.2. And this is gonna come out weird because I used like 2 different problems, so you would never, you're probably not gonna have an efficiency over 100%, but this problem is because I made it up.
2,500.
Yeah, okay? So it's energy out divided by energy in times 100. And our energy out is the mechanical power. Energy in is the electrical power, and then times it by 100, okay? So the mechanical power was, what was it, 54.8?
Yeah, 54. No, 42. No, 54.2.
Thank you, 54.2. And then divided by 0.024, and then times it by 100, and you're getting over 2,000%. You won't have one like that on the test. 200,000.
I didn't get a chance to multiply it by 100.
Yes.
It was already over it.
Okay, so what is it?
200.
Okay.
Alright, I can't write.
For a-
225,833 percent. Okay, impossible, but that's because I made it up on top of my head. So, okay, good. You can write all that you want.
Yes, watch what I'm saying. It's like, I like when you can just do it as right. I don't do anything. I don't like this. Yo, Justin, what you do?
I'm sorry. Wait 1 second. Let me get this stopped real quick.
Oh, Eli, have you tried?
Maybe if I can.
It's